So in last lecture we have seen that this moment of inertia is nothing but tendency of the body to resist the rotational motion, and mathematically it is written in a form I is equal to mr square. So the moment of inertia in a rotational motion is equivalent to the inertia in the linear motion. We have also seen that this moment of inertia depends on the total mass of the body, distribution of the particles about the axis of the rotation. It also depends on the shape and position of the axis of the rotation. Now in this lecture we are going to see what is the moment of inertia of a spherical shell about its diameter. Consider a spherical shell like this. Let this be the axis of the rotation, which is the we have considered as a diameter. So consider the spherical shell which is rotating about its diameter, any of its diameter. Let r be the radius of the spherical shell and m be the mass of the spherical shell. Then I am dividing this spherical shell in thin slices which are bounded by the two surfaces. Let's call them EF and GH. So this spherical shell is divided into a thin slices bounded by this EF and GH. Now this will be a thin slice of this spherical shell, and if I see this from the front side, or if I rotate it by 90 degrees on the left hand side, so I can see clearly a thin ring like this. So let the distance of this slice from the origin O be x. So this is the axis of rotation now, O dash, or we have called the center as O. So let's call it as a x dash. And if we are seeing this slice from front side, so the x dash is passing through this point. So this is point O, and x dash is passing through this point. Let dx be the width of the slice. So this is width of the slice dx. So this distance is dx. If I calculate the moment of inertia of this thin slice, and if I integrate it from this minus r to plus r, then I am going to get the total moment of inertia of a spherical shell about its diameter. So let us try to calculate this. So the things which we have considered is m is the mass of the sphere, capital R is the radius of the sphere. Then let x be the distance of the slice, from center, and dx is the width of the slice. Now if I call this point as say S, so if m is the mass and r is the radius of the sphere, then mass per unit area of this whole sphere can be written as m upon 4 pi r square. Now area of this slice is 2 pi into r into dx, where r is the radius of the slice and this dx is the width of the slice. Mass of the slice can be given by m upon 4 pi r square multiplied by this 2 pi r dx, so which will give us m upon 2r dx. So let the mass of the slice be dm. So mass of the slice is calculated by mass per unit area of the whole sphere multiplied by the surface area of the slice. So this will give us the mass of the slice, and which we have considered it as a dm. So this dm is given by m upon 2r into dx. Now according to the geometry of this triangle, say OE and S, so in this triangle we can write, now consider this as an angle theta. If this is angle theta, so this angle will be also theta. Okay, and this small angle from E to G. So if this angle is theta, then the width EG is given by R into d theta. And in triangle OE and S we can write, so this is angle theta over here. You cannot see just here because this diagram has become very small. Okay, but this angle, consider this angle as a theta and this angle as a d theta. So if this angle is a theta, then in triangle OES we can write sin theta is equal to OS upon ES, and cos theta is equal to ES upon OE. So this OS is nothing but x upon OE, which is sin theta. And in this diagram we know that this OE is nothing but r. We can put the value of this OE also r. So cos theta is equal to ES upon r, or we can write x is equal to r sin theta, or we can write, so this, if I take a derivative of this x, so I am going to get dx is equal to r cos theta into d theta, and here we are going to get this ES is equal to r cos theta. I can write it here ES into d theta as a dx. Also in same triangle OES, by using the Pythagoras theorem we can write, so this OE square is equal to OS square plus ES square. ES square is equal to OE square minus this OS square, which is equal to r square minus x square. Now let me call this as a equation 1, this as a equation 2, and this as equation 3. Now the momentum of inertia of this thin slice about the axis OO dash is given by moment of inertia of a slice. So let us call it as a I into S. So the moment of inertia of this slice about the axis of the rotation OO dash is given by mass of the slice multiplied by the distance from the axis of the rotation. So in this case the distance from the axis of the rotation is E into S multiplied by this ES square. So dm we have calculated, which is in equation number 2, so which is m upon 2r into dx and multiplied by es square is nothing but the r square minus x square. So this is the moment of inertia of this small or the thin slice about the axis of the rotation x dash. Now if I take the integration of all these thin slices running from this minus r to plus r, I can get the total moment of inertia of the spherical shell. So this I is given by integration of this is running from minus r to plus r, and it can be also written as 0 to r into 2 times of this is. If I am taking the integration from 0 to r 2 times, this will also give me the momentum of inertia of a spherical shell about its diameter. So let us integrate this whole term. So it will be 2 into integration of m upon 2r dx r square minus x square. So this I is given by 2 into, therefore I is equal to 2 by 3 mr square. So if you want to calculate the momentum of inertia of any body, any rigid body, you just have to make thin slice of it, take momentum of inertia about the given axis of rotation of that thin slice, and then you have to integrate the term to get the momentum of inertia of the whole body.